and I asked in the, so I just started, right? And for the pure substance, we just showed that how the degree of freedom will work. And let me recap what we actually started. Multi-phase multi-component. Multi-phase multi-component. Okay. So we have G, we had P x1 to xc minus 1, independent value. And how many unknowns are there? C minus 1 plus 2, C plus 1. C plus 1 unknowns are there. So C plus 1 independent unknowns. Earlier I defined degree of freedom. Number of independent unknowns minus number of independent algebraic equations, it gives the degree of freedom. And you have seen that degree of freedom at determines, if it is 0, you get unique solution. The degree of freedom is non-zero, you get multiple solutions, infinite number of solutions. But number of degrees of freedom will tell you that how many variables you can fix so that you get unique solution. So for the multi-component substances, we have number of components C, number of components C, and number of phase, I am saying pi. Number of components C, number of phase, I am saying pi. So pi number of phases, we are having pi number of phases. So for two phases, first phase and second phase, what we write? T1 equals to T2. If another phase, third phase, we have equals to the first and third, second and third, and whatever. So we can write another equation as T2 equal to T3. So if there are three phases, we get 2T equations. We get 2T equations. Similarly, in the three phases, we get 2P equations. Independent equation. You can get third one also. That is not independent. Okay, these two are independent because you said T1 over T3. That is quite obvious if you go T3. Okay, so out of that two are independent equations. So these are the independent equations. Independent equations. Right, these are two are independent equations. So if we have pi number of phases, how many independent equations will get from T1? We will get T1 equals to T2 equals to T pi. But that will be obtained from how many independent equations? Yes. Pi minus 1 independent equations. Pi minus 1 independent equations. Similarly, P1 equals to P2 equals to P pi. Again, pi minus 1 independent equations. For this type of systems, when you look at the thermodynamic equilibrium, remember that when you have thermodynamic equilibrium, for that when I give the Gibbs statement of thermodynamic equilibrium, the pure substance and two phase. If you can recall, we started from the mu, that is capital G, which is Tp and n, function of Tp n. And from there we found that T1 equals to T2, T1 equals to T2, mu1 equals to mu2. That is the pure substance. By using the same optimization concept, and how did I get it? By setting the optimization. Because if you have f is the objective function, x vector, you have to have grad f. Grad f equals to 0. Grad f means what? F of grad dou f by dou x1, dou f by dou x2, and dou f by dou xn. Okay. That's the objective function. So for this case, for multi-component substance, we have function TEP C N1 to NC. Right? That is the way you start. If you follow that, if you look at please turn your notebook, just see how we have done the pure single component two-phase thermodynamic equilibrium. You have the notes with you? You have the notes with you, right? Actually, we have done with internal energy or the display energy. What we have done? Anybody can tell me? Internal energy. Internal energy has to be minimum. Okay. So you can take this one, or you can take, better to take as internal energy, which is U S V N1 to NC. These are same equivalent. Either you take this one or G. If you take this one, you know the criteria. Minimization of internal energy. Right? Minimization of internal energy and maximization of what? Entropy. Entropy maximization, minimization of internal energy. So either take this. So this equation, if you talk about TEP x1 to, or if you say capital G N1 to NC, is equivalent to this. Or capital U. Capital USD. No problem. Equivalent, right? Because this can be obtained from region transformation. So you cannot say that G equation is independent of U. And what it will give? It will give, if you do this grad F, that means grad U equals to 0, we will get T1 equals to T2, then P1 equals to P2. That is already done for the pure substance. And single phase is TDN, right? That is mu. And what we have is N1 to NC. That means you will get mu1 equals to mu2 I, where I equals to 1 to T2. That's extension of your so the extension of for pure substance, extension from pure substance to multi component substance. Extend from pure substance to multi component substance. So now coming back, so we have now you know now what are the conditions, what are the algebraic equations, independent algebraic equations we have. Okay. So we have for each component mu I1 equals to mu I2. There are pi number of phases. So how many such equations will you get? C equations for each I component. C equations for each I component. Sorry, one equation for each I component. So C number of total equations. You get C number of total equations. And this will be there for each component pi minus 1. So pi minus 1 into C. So total number of algebraic equations. What we have? Total number of algebraic equations. Total number of algebraic equations independent. We can write independent here. Pi minus 1 plus pi minus 1 plus pi minus 1 into C. So it is how much? Pi minus 1 into C plus 2. It is then, if you take everything out, degrees of freedom, degree of freedom. Number of independent algebraic equation is pi minus 1 c plus 2. So pi minus 1 c plus 2, then minus number of pi okay pi into how much is coming? C minus pi plus 2. That's what we have done earlier. But this is the first time we are proving it. You prove it earlier, Rahul, the first time. C minus pi plus 2. Please look at the more foundation of this proof in Professor Ravi's IITC paper just published. He just published. He talks more on that on this paper. So F equals to C minus pi plus 2. Okay. So now this is the foundation we'll talk about. So generally speaking, when we talk about algebraic equations, T and P generally fix. If you fix T and P, only you have to worry about mu I1 equals to mu I2 or mu I1 equals to mu I3, whatever. So the main concern of our algebraic equation is this equation. When temperature pressure is fixed, then only matter of concern is mu I1 equals to mu I2. So let's look at the overall phase equilibrium or overall phase equilibrium for the multi-component substance. We want to do for chemical engineering application vapor liquid equilibrium. So we'll talk about VLE, vapor liquid equilibrium. We'll talk about VLE. We'll talk now. We'll talk now VLE. Vapor liquid equilibrium. Basic equation. So we'll have vapor liquid only two phase, but we have multi-component. We have only two phase, but we have multi-component. So multi-component substance distributed in vapor and liquid phase. And I will show you. So first we will talk about T1 equals to T2. Vapor phase, liquid phase, P1 equals to P2, and then mu I1 equals to mu I2 for I equals to 1 to 6. We'll always worried about this equation. This two are straightforward. Okay. So now we'll show the right time this chemical potential, as I mentioned, in a pure substance, single phase, we cannot measure chemical potential. And we going to determine fugacity, right? Or fugacity coefficient for the pure substance. Multi-component substance, same way, we cannot determine chemical potential, but we know how to determine fugacity. Let's talk about the multi-component fugacity, and we know how to determine multi-component fugacity earlier. So we know that mu I minus mu I IgM Tp x bar, which is the definition of fugacity, at T ln Fi by P xi. And it says mu I equals to mu I Igm plus Rt ln Fi by P xi. Okay. And it is, if you talk about the functions, mu I Tp x bar, which is mu I Igm Tp x bar plus Rt ln Fi by Px. So far everything is fine. So I am doing all the old thing. These are the kind of things already discussed. And we can also write this mu I Igm Tp x bar. There is a relationship. Mu I Ig Tp plus Rt ln xi. We have done it already. Correct? We already done it. So far nothing new I have done. I am just talking about derivations. Our objective is if mu I1 equals to mu I2, what can we talk about the fugacities for ith component in 1 and 2 phase? That's what our objective. Let's look at more of that. So at equilibrium, mu I1 equals to mu I2. So we have mu I1 Tp x bar, which is mu I2 Tp x bar. Equilibrium is temperature, both side temperature is same. That is already established. That advantage. Both side temperature is same. And mu I1 you can write as mu I1 IgM Tp x bar plus RT ln Fi1 Pxi1. Right? Yes. P is the same, P1 and P2. So I can write P. So it is mu I IgM 1 IgM Tpx1 plus RT ln Fi1 T, just write the functions better, x bar I by Px Pxi equals to mu I2 is mu I 2 IgM Tpx2 plus RT ln Fi2 Tpx2 divided by Pxi2. Am I correct? Yes. Now mu I 1 IgM we can write in terms of Ig. That is mu I 1 Ig. Mu I 1 Ig. When I say Ig is Tp plus RT ln Xi1, right? Plus RT ln Fi1 Px bar 1 by Pxi1 equals to mu I2 Ig Tp, same way RT ln Xi2 plus RT ln Fi2 Tpx bar 2 by Pxi2. I'm just putting from here to there. What is mu I1 Ig? That's called pure component, ideal gas. At P tending to 0, ith component is there. This is at P tending to 0, ith component there, only change in phase. Okay? Only change in phase, doesn't matter. Okay, so only change in phase is there. So we have. So what actually you can comment? Huh? Both are equal because at P tending to 0, this is pure component, pure ith component. You can write pure ith component at P tending to 0. Doesn't matter. Same. Okay. IgM is different because IgM depends on many things, so we cannot talk on. So you can actually cancel. Why IgM is different? Because if you look at that IgM has this entire thing. If you say IgM, the function of Xi also. So Xi in first phase is not equal to second phase. So only you can equate Ig. Okay? It's only function of temperature and pressure. Nothing else. It's not a function of temperature X bar. But IgM is a function of temperature, pressure and X bar. And X bar, X vector in a first phase is not equal to second phase. Right? Correct? Okay. So, what will happen? So that these two are cancelled. If you plug it in, this xi1 xi1 will get cancelled, xi2 xi2 will get cancelled. Okay, so R and T will be both cancelled out. R molar gas constant temperature is same. So what you look at? Fi1 Tp xi1 equals to Fi1 Tp xi1 Am I correct? This P and P will get cancelled. This P will be remaining, but you just take the log out. So what will have? Fi1 Tp xi1 by P was Fi2 Tp xi2 by P, and P will get cancelled. So you get, this is the alternative equation for VLE, which replaces mu I1 Tp x bar equals to mu I2 Tp x bar. Right? Clear? So for the multi-component multiphase, your equations are temperature equal, P1 equal to P2, P1 equals to P2, Fi1 equals to Tp xi1 equals to Fi2 equal to Tp xi2.
So is a function of xi alone or
X bar, sorry, thanks. Okay, so we'll now take we can actually go on different equations. First we talk about the binary mixture. C equals to 2. Binary mixture, because I am saying the vapor liquid equilibrium. So pi must be 2. I am doing only vapor liquid for chemical application. I am not doing anything else. That's on this syllabus. Vapor liquid equilibrium. C equals to 2p, pi equals to 2. I am saying that X denote mole fraction in liquid phase. Y denote mole fraction in vapor phase. X component, X bar denotes mole fraction in liquid phase, Y bar denotes mole fraction in liquid phase. Now tell me, what are the unknowns for the binary mixture? What are the independent unknowns for the binary mixture? What are the independent unknowns for the binary mixture? Can you tell me the variables? What are the independent unknowns for the binary mixture? In vapor liquid system, equilibrium. In the vapor liquid equilibrium, two components are there. That's a very common in chemical engineering. Binary mixture. What are the unknowns? Independent unknowns. You have got the clear cut concept by now. Not you. Somebody else? Yes? Pardon? Not TP, T1, T2, P1, P2, then please look at your notes. We have done that. We have done it today morning. What are the unknowns? I want the variables. Not x1 bar is not there. x1 bar, I don't have any such variable for x1 bar. What is that? You don't ask them, if you are not sure, then don't talk. People are there, I will discuss anyway. x1, here y1. Because we know that TP x1 to xc minus 1 are the independent unknowns. Okay? C is 1, C is 2, so it should be only x1. Similarly, it is replaced by x2. But thing is that I don't have x and 1 because I say that xi is nothing but x and x2 is nothing but y vector. So I don't write x. I don't want to write any superscript. Only x means mole fraction liquid phase, y means mole fraction vapor phase because I have two phases. So in that case you are lucky. You have two phases, but you may have multi-component. Two phases you can easily handle, no problem. So you have got 6 variables. How many independent equations we have? We have independent equations for here, for pressure and for the chemical potential. So how many independent equations we have? How many independent equations we have? Not trouble. There are 6 unknowns. How many independent equations we have? Just now we have done. Just now we have done. What are the independent equations, madam? What are the independent equations? Not you. What are the independent equations? Just the morning you have done. I am doing very simple. Morning I have done very complicated stuff. I am asking binary mixture two phase. How many independent equations we have? I want the equations, particular equations. Do you have them? Can you tell me the equations? P1, you first chose P1 equals to P2. What is that? P1 equals to P2. Mu1 I to mu2 I. Then mu2. That's all. Right? So you can see that there are 6 unknowns, 4 algebraic equations, and your degrees of freedom is 2. That is also from your formula, C minus 5%. The formula also gives that. These things are already fixed. So what we will be talking about? Mu I P x bar equals first phase. You can say mu I liquid phase, mu I vapor phase, P. This is my equation. So entire equation, all algebraic equations will boil down to one simple unified notation. This is not a single equation. It is 2 equations. There are 2 equations, but I can have entire algebraic equations, the domain, into a single format. And T and P is taken care. If T and P are not taken care, you have to write extra. And T and P are taken care because they are the equilibrium. It is not equilibrium, different issue. I won't talk about. So the vapor equilibrium problem. And equilibrium we always talk about in chemical engineering because at the equilibrium separation is maximum. That's why we talk about why I go for non-equilibrium. I don't want non-equilibrium for the chemical engineering because go distillation, mass transfer, separation process, whatever. Bleaching, liquid extraction, the equilibrium state we want because that will give the maximum separation process, and that's what we want to go for. Vapor equilibrium. Right? Okay, so and this means that you have to solve. This is alternative representation you have, which is FIL PP x bar equals to FIV PP x bar. Right? FIL equals to FIV PP x bar. The criteria for equilibrium. Okay? So now I will first. So now challenge is how to solve this. For binary mixture is okay. If you have multi-component mixture, vapor liquid, you need to solve this. So it also says that the degree of freedom is 2. Either you can fix temperature. So here we can fix temperature or X or pressure, Y, whatever. 2 variables. You are free to choose. We will discuss some numerical problems as I given your as problem set number 4. We will discuss how to use this concept and get all the problems solved. So for this case, where you can easily see that we can have different degrees of freedom and we can actually easily handle. So first we'll be talking about the how to solve for low pressure. That is always better. You might have heard something called Raoult's law. Raoult's law. Did you know how to derive Raoult's law? Or you knew by definition? You knew by definition. What's about you, madam? By definition. So I derive Raoult's law from this. So Raoult's law is a consequence of vapor liquid equilibrium. So I derive Raoult's law for Fi equals to Fi equals from Fi equals to Fiv. Let's look at, so I am talking about so that means if I derive a low pressure situation, so first assumption in Raoult's law, it is valid for low pressure. It is valid for low pressure, both in liquid phase and vapor phase. Otherwise you cannot have Raoult's law. So let's look at how we can actually establish or develop Raoult's law. So for liquid phase, for liquid solution, liquid phase or liquid solution, solution is mixture, mixture is a liquid solution. We refer as IS, ideal solution, at T tending to 0. Vapor phase, so liquid, vapor phase we refer as gas mixture. We refer this as what notation? Gas mixture at P tending to 0. What notation you refer? IgM, ideal gas mixture. IgM at T tending to 0. So at P tending to 0, vapor gas mixture will behave as IgM. The question is whether IgM behavior and IS behavior are the same. For some aspect they will be same, but they will differ. They will differ. Okay. So let's see IgM versus IS. IgM versus IS. Ideal gas mixture versus IS. So for IS, IgM we have resolved it. IgM we have resolved it. We remember that we started with the fundamental relationship equals to mu t equals to mu 0 t plus RT and P long back, and then from there we have derived. So that part is resolved. IgM part has been resolved by the Gibbs. IS, the basic rule will follow Lewis Randall rule for ideal solution. For ideal solution, we will have the Lewis Randall rule. Okay. So for fugacity of component of I in solution, Fi(Is) is equal to the what is fugacity of I component of ideal solution with the Lewis Randall rule says that Xi Fi star. So fugacity of component I in ideal solution, which is fugacity of component I, fugacity of component I in ideal solution. Okay, this is a pure component fugacity. It says that an ideal solution Fi is nothing but Xi Fi star, the Lewis Randall rule. You might have seen earlier. So Lewis Randall rule says that fugacity of I component ideal solution is nothing but Xi Fi star, where Fi star is a pure component fugacity. What actually happens for multi-component Fi IgM? Because we are talking about IgM versus IS. We are talking about IgM versus IS. IgM will be what? IgM. Fi by Pxi equals to that mu I minus mu I. IgM is there, right? What is that? Am I correct? Yes. So that means this fugacity is based on the gas mixture. This fugacity is defined, very important concept, defined for gas mixture, because it talks about departure from ideal gas mixture, not from the ideal solution. And what it says that if P can equal to 0, Fi IgM, it will be Pxi. Correct? So Fi IgM should be equal to Pxi. Correct? Because fugacity is defined based on the gas mixture. Okay. So similar to IgM, similar to IgM, you can also write mu I is as mu I star Tp at T ln xi. This is analogous to what? Mu I IgTp. Am I correct? Mu I IgTp. So up to that everything is okay. Only except this relationship. Because we have Fi equals to Pxi. Lewis standard rule says Fi is equals to Xi Fi star. Because remember that fugacity is based on the gas or gas mixture. Because the definition is based on gas or gas mixture. You cannot say, oh, Fi is equals to Pxi. It's not. Because we don't know what the departure of mu I minus mu I is. Is it equal to mu I minus mu I j? We don't know. So, and also the basic definition is there for the Lewis standard rule we have to apply, which is if Fi is equals to Xi Fi star. Now the question is, when you talk about the Is and IgM, and these equations are actually valid, what is the Vi bar Is? What should I write here? Okay, IgM equals to Vi Ig. That we have already proved. If I write Vi bar Is, what will be right hand side? Ig I cannot write. Ideal solution. And solution means if I have only one component, I can have only one liquid solution. One component. One liquid. For example, water. Pure component, only one component. Now I am putting ethyl alcohol. Water and ethyl alcohol. So like that I am talking about. For gas mixture, nitrogen, oxygen. These are the ways we talk about the gas mixture. So what will the right hand side proper symbol? If you look at the board, what will be the proper symbol? Vi star. Yes, you are right. Vi star. How to prove it? We have done the proof here. How to prove it? How to prove? Can you follow the similar way to prove it? What we have done for the IgM? How did you prove for IgM? Can you help me? And I will see whether you can do by similar way. How did you do for the proof for IgM? How to prove for the IgM? For IgM we have proved it, right? Vi bar IgM equals to Vi Ig. Vi bar IgM equals to Vi Ig. We have proved it. How to prove it? Yes, what's the first step? What equation will it attack with? We have done the notes. So who can actually? Yes. What is that? How do you prove Vi bar Ig equals to Vi Ig? That's what I'm asking, madam. Vi bar IgM equals to dou mu I IgM by dou P N bar. Can I write this as for Is? Yes or no? Yes, why? Because you skip some of the steps. That's the thing, if I skip the steps, you will feel sir is bad. You can skip, you have the power. I don't have the power. So I won't use this step as the first step. I won't use the first step. So mu I Is is my first step, which is mu I star Tp plus RT ln xi. And we have dg equals to minus sdt plus vdp plus r summation I equals to 1 to c mu I dni. This is similar relationship because mu I IgM plus mu I Ig Tp plus RT ln xi. Okay, now I have mu I equals mu I star Tp plus RT ln xi. And mu I mix from here, which is dou g. See, so much of concept. You guys think only mathematical manipulation. If I do that, you'll complete lost, right? So much things. Dou g by dou ni, which is Tp Nj, j not equals to 1. Equation number 8. And from here, we can actually find out. From here, dou mu I mix by dou P Tn bar. I am just following exactly what you have done earlier. What is the next step? Dou mu I mix equal, so you have to put that, which is dou V by dou Ni T Nj, J not equals to I, which is Vi bar. This exact thing is already valid, whatever we have done earlier. Now Vi bar Is, which is dou mu I Is by dou P Tn bar. Okay, so we have seen that it is verified from here. We have verified this for earlier mu I Ij, but it is now verified from the all definitions. Everything is intact. We can write mu I Is T bar, and then what you can write, mu I Is equals to mu I star Tp plus Rk and Xi. Okay, so what it will give? This will be this mu I Is can be substituted. Mu I Is is nothing but mu I star Tp plus Rt ln Xi. You substitute, you will get Vi star. Similarly, but with temperature derivative you will get, what? Si bar Is equals to Si star yes, what it will be? Is Si star? Am I correct? Then it is not Si star. So that means if I write something, we will accept it, right? Accept problem. What is the proper form? Si star? Not now. Minus please prove it at home. Ui bar Is equals to Ui star and Hr bar Is equals to Hi star. So similar kind of behavior one can actually expect, and Gi bar Ij already I have given, which is this Gi bar Is. Gi bar Is is nothing but Gi star plus Rk and Xi. Already there. Gi bar Is is already there, which is Gi star plus Rt ln Xi. So far Ign and Is everything is fine. Only problem is Lewis standard rule. Because definition of fugacity for the liquid system, we cannot go by just similar to the vapor. If you can write this for the Fi by Pxi goes to mu I minus mu Is, you can do that, but you cannot do. Why? Because at P tending to 0, Fi cannot be equals to Pxi. What I am saying that Dalton's law of partial pressure. Dalton's law of partial pressure is valid for the gas mixture. Is it valid for the liquid? No. That's why you cannot write. So this definition has some rational, some kind of physics. Because if you look at pure substance, which was defined as Rt ln F by P, mu minus mu Ig, this is not a gas mixture. For liquid, we cannot write, because if we write that this fugacity is equal to pressure, it is something, and of course that will be grown up for this kind of gas mixture. That will be grown up for the gas mixture. So what actually happens? We have FIL equals to Xi Fi star Lr, Lewis standard rule. Okay. We have FIB equals to what? FIB will be FIB equals to, we have done just now at low pressure, equals to P into YI. See, you don't even follow the class. P into YI. So we have, and what is Fi star? Pure substance fugacity. For pure substance fugacity, how to find out Fi star? Pure substance fugacity, you could find the Fi star. Do you remember that saturation pressure? So pure substance fugacity is nothing but saturation pressure, neglecting Poynting correction. We have done earlier. We have done earlier that F by P that we have calculated with the Poynting corrections, and if you look at that pure substance fugacity, nothing but the Pi saturation pressure. Okay, so when FiL equals to FiV, which is nothing but Xi Pi sat equals to Pi, which is the partial pressure. Partial pressure denotes in the gas phase. Partial pressure is not defined in the liquid phase, the gas phase. It is nothing but Xi Pi sat saturation pressure, which is obtained from your Poynting correction or whatever. In your this diagram, whatever we have this diagram, we have proved something, right? So this kind of thing will give Pi sat, and this is nothing but Raoult's law. Thanks for kind attention.